Gravitational force is the most obvious force that acts on every object on Earth that has mass. Gravity is that force that governs the movement of celestial bodies. It is a force that doesn't require a need of any intervening medium, meaning it is a non-contact force. All the other forces that are common in mechanics are contact forces. The term force is quite straightforward. It just means a push or a pull. But when you observe an object, the number of forces acting on it is not that straightforward as you may think. For instance, consider a box of some mass m kept on a flat surface and the box is pushed with some force F. How many forces do you think acts on the box at that particular instant? Here, see for yourself. These many forces act on the box at that particular instant. It may seem a little complicated at first, but moving forward, the seemingly hectic job of identifying forces will be a piece of cake. When a box is simply at rest on a table, Earth's gravitational force pulls it downward, which is termed as the weight of the box, given by mg. All of this force exerted by the Earth on the box, but the box doesn't fall down through the table. Why? Some other invisible forces must be present to balance the effect of the other force. This is the normal reaction force that is exerted by the table on the box opposite to the direction of the force of gravity. The force acts normal to the surface of contact, hence the name normal reaction force. Now we apply a small force F on the box in the horizontal direction. But this small force is not enough for the box to move. It stays put. However, if no other forces are acting on the box, it must move with an acceleration F by m, no matter how small the applied force is. What is going on here? Again, the next invisible force present here is the frictional force or friction. More precisely, static friction. As soon as you start applying a force on the box, static friction opposes the horizontal motion. It acts on the box directed opposite to the applied force in order to maintain a zero net force. One fascinating detail about static friction is that it only comes to play when some force is applied. When the applied force is increased, the static friction also increases up to a certain limit and tries to equalize with the applied force. We can define the static friction like this. Static friction is a type of frictional force that opposes impending motion. The term impending motion means motion that would take place under the applied force if friction were absent. The limiting value of static friction is experimentally found to be proportional to the normal reaction force and independent of the area of contact. That is, Fs max is equal to mu s times n, where mu s is the constant of proportionality called the coefficient of static friction. It depends only on the nature of the surfaces in contact. So the law of static friction is written as F is less than or equal to mu s times n. This means that when the applied force is greater than the maximum static force, the box begins to slide on the surface, thereby starting to move. Now, if you apply a force greater than the maximum static friction, the box moves. Once the body is in motion, it is subject to sliding or kinetic friction, which opposes the relative motion between the two surfaces in contact. Frictional force that opposes the relative motion between the surfaces in contact is called the kinetic or sliding friction, and it is denoted by Fk. Just as static friction, kinetic friction is found to be independent of the area of contact. Also, it is nearly independent of the velocity. It satisfies a law similar to that for static friction. Fk is equal to mu k times n, where mu k is the coefficient of kinetic friction and depends only on the nature of the surfaces in contact. Experimentally, it is found that mu k is less than mu s. When relative motion has begun, the acceleration of the body according to the second law is F minus Fk by m. For a body moving with constant velocity, that is zero acceleration, F equals Fk. If the applied force on the body is removed, its acceleration is minus Fk by m, and it eventually comes to a stop. Practically, this is not possible. While rolling, the surfaces in contact will suffer from a momentary deformation. This results in a finite area of the body being in contact with the surface. The net effect is that the component of the contact force parallel to the surface opposes the motion. This force that opposes the rolling motion is called the rolling friction. Generally, for the same weight, rolling friction is much less than the sliding or static friction. Friction is considered as a dissipating force because it opposes the relative motion and often causes wastage of energy. There are different ways to reduce the friction. That is by applying lubricants, inclusion of ball bearings, maintaining a thin cushion of air between the two surfaces in relative motion, etc. are some of them. But friction is useful in certain situations. As friction is a force that opposes a relative motion, it is made use of by brakes in automobiles. Friction, although we say in general oppose motion, it helps us to walk and play an important role in the motion of tires of vehicles on a road. Now, let us put the friction story aside and discuss about the two other common forces in mechanics, that is the tension and the spring force. Friction is a contact force. Now, if one of the objects in contact happens to be a string, rope, cable or spring, we call the force as tension. It is the pulling force that is transmitted axially along the string or rope. Very similar to tension, when one of the objects in contact is a spring, depending on the amount of compression or elongation of the spring, a restoring force is generated inside the spring. This force is called the spring force. Spring force is proportional to the change in the length of the spring made by the stretching or compression. Solving a problem in mechanics will require us to analyze the forces present in the object under consideration. Have a look at this image and try to analyze the number of forces present here. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.